Okay, here we go. Computer numbering systems. Yesterday we established why we need to use them. Of course, the computer is digital. It can only represent two states, 0 and 1. And this maps very well to the binary numbering system, where we have only two values, 0 and 1. But we have the need, we as humans, of course, we communicate, we understand decimal very well. And that's actually part of the problem. We understand decimal so well, we've forgotten the algorithms that we learned decimal with. And that's what we have to revisit. We have to understand decimal from an algorithm standpoint. So let's begin. This is the 02 binary computer numbering systems worksheet. I did ask that everyone did that 01, that computer numbering systems introduction prior to this. So let me ask the first question. What do we know about decimal? Can someone tell me, what do we know about decimal? What was that? 0 to 9. So you gave me the lexicon, or the universe of digits. So I'll write that down. 0 to 9. What else? Well, how many symbols are there? 0 to 9, total number of symbols, 10. So we're talking about base 10. Anything else? What about that 0 to 9? Is it ordered? Okay. Yes, it's ordered. Okay, so I know that 1 is greater than 0, 2 is greater than 1. By transitivity, 2 is greater than 0. So we understand this. Okay, good. So now we need to develop an algorithm of how we count in decimal. So how do we count in decimal? Can someone tell me how we count in decimal?
Cross that barrier with the 9, we start using the multiple symbols from that lexicon, 0 to 9, continuum.
So it's actually a more comprehensive analysis than I usually get. Normally, someone will say, oh, we go 1, 2, 3, 4, 5, 6, 7, 8, 9. They'll give me an example, which is perfectly valid. Quite often in programming and information systems analysis and design, we actually start from an example and we extract the patterns. And then we use stepwise refinement. It's very rare that we get it right or entirely correct out of the gate. So slowly we improve our algorithm. Okay, so you stated we move from one number to the next. We add 1, right? And what do we start with? Because that's actually the starting point. What do we start with? Start. Okay, so I'll create a label here, start. Start with 0. Okay, and I may come back and address that in a minute because I may qualify it further. So what do I do next? How do I get from 0 to 1? Add 1. But in a generic algorithm sense, I'll say next. I'll use an arrow just for pseudocode here. If I can draw an arrow. Next gets current plus 1. And this is fine until we get to what? Up to 9, right? 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1. And then we kind of hit a roadblock, so to speak, when I get to 9, 9 plus 1. And I could code this as 9, but what is 9 actually? Generically. It's hard. It's hard extracting this. It's the last one in the sequence, the last one in the ordered sequence, because I want to make this generic, because once I have this algorithm developed, I can apply it to any numbering system. So if last in sequence, I can type, what do I do? If it's the last in sequence, what do I do? And again, go from example. What do we do? 9 plus 1. What do we do when we add 9 plus 1? Okay, now you're moving left to right. That's because, again, this is what everyone does. We've become so good at this analysis. Our brains just kind of jump to the end result. But when we were taught, in first, second grade, or whenever, 13 plus 1, I added 1 plus 3, 4, and then went to the tens place, right? We were taught to add right to left. And that's what we have to force ourselves back into, the way that we learned mathematics. So, yeah.
So you would basically restart the sequence and then move to the next largest digit.
Exactly. Right. So I'm going to go to start and carry the 1. Right? And I'm carrying 1 to the next highest positional value. Okay? So that's essentially it. Now something implicit here, when we start with a 0, we're always starting with 0 in that least significant positional value, aren't we? And I say that because we don't even think twice about that in decimal, right? 19 plus 1. 9 plus 1 is 0, carry the 1. 10 plus 1, 2. Okay, 20. In addition, same thing, 13 plus 1. Everyone here is thinking 14. Nobody here is thinking 23. But for some reason, when students first learn binary, they will make these types of mistakes. 17 plus 1, 27. We wouldn't even think of doing that, but this will occur. So again, we have to force ourselves into using the algorithm. Start with 0, and that will be the least significant digit. So I'll just use LSD kind of incorrectly because LSD is also least significant denominator. Okay, so what we're going to do now, I'm going to kind of move everyone out of their comfort zone and force you into using the algorithm. We're going to count in tertiary, so please get out paper and a pen. I'm going to purposely move slow, so please move in advance of me using the algorithm. So if we're counting in tertiary, my lexicon or universe of digits, I'm going to use 0, Q, and T. I just chose these arbitrarily. And we must acknowledge that back in decimal, 0 through 9, at some point in time, probably by consensus, people chose these symbols. 0 to denote 0. That symbol, that is the 1 to denote 1. So I've just arbitrarily chosen 3 symbols, O, Q, and T. And I'm going to count in tertiary. And I'm going to move slowly. Please move in advance of me if you can. And you should be able to. So what do we start with? I start with O. I hit return. Microsoft Word will capitalize it, make it look like a 0. Sorry about that. O plus 1. Or in this case, it would actually be O plus Q, right? Q is 1. O plus Q, or 0 plus 1, in this lexicon would be Q. No. We're making this up as we go, as a teaching tool. Q plus 1. Is there anything left in that lexicon? Yes, there's something that corresponds to T. So Q plus 1, or actually in this case it would be Q plus Q, of course, would be T. And now we get to where the fun begins. T plus 1, or in this case, T plus Q. And again, I'm sure at least half the class will move left to right, but our algorithm states we should move right to left. T plus 1, well, is there anything for 3? No, right? So I record the O, I'll move my cursor backwards, and what is 1? Q. Okay. QO plus 1. What is QO plus 1? QQ, correct. We're moving left to right. O plus 1. Think about it. This is what I just said. People will make that mistake. 13 plus 1. 3 plus 1 is 4. 1 plus 0, of course, is 1. People want to add that 1 to the Q or something. What is O? O is 0. What corresponds to 0 plus 1 is Q, Q, Q. And then again, I should have done that right to left. QO plus 1, O plus 1 is Q, and of course I bring down the Q. This is no different than 13 plus 1, right? 3 plus 1 is 4. I bring down the 1. Okay? If you're struggling with this, you're not letting go. You're not following the algorithm. And that's what you have to do. You have to relearn what we were taught when we were 3 years old, when we were 4 years old. And unfortunately, our brains have progressed so far, it's sometimes hard. Okay? QQ, okay? And I know that's 1, 1 in tertiary, or the equivalent of it, plus 1. Again, I'm going to move right to left. Q plus 1, what's the next one in the sequence? T. So I'll put the T down, and I'll move my cursor to the left of it. Q plus, of course, 0 is Q. And we're to another one of those points. QT plus 1. Well, moving right to left, T plus 1. Is there anything for 3? No. So I write down the 0, or the O in this case, and I carry the 1. Q plus 1, T. I'll take this out just a little bit further. TO plus 1, O is 0, plus 1 is going to give me the next one in the sequence. So in this case, I see it. I'm going to take that leap. I'm going to move left to right. TQ. Right? O plus 1, what's the next one? All I did, this is the same thing as 0 plus 1. I'm just using different symbols. I'm forcing everyone out of their comfort zone, because once you can do this, you can do it in base 4, you can do it in base 5, you can do it in base 6, in any base whatsoever. Okay. TQ plus 1, Q plus 1, Q plus 1 is 2, or in this case, the lexicon is T. And of course, as T is nothing to add to, so the answer is going to be TT. And this next one, I'm going to stop after this next one, because in decimal, it would be the equivalent of adding 1 to 99, right? 99 plus 1. 9 plus 1 is 0, carry the 1. 9 plus 1 is 0, carry the 1. So if I were doing this, T plus 1 is 0, carry the 1. T plus 1 is 0, carry the 1, and the 1 is going to be Q. What's that? Well, there's zeros there. Yes, my keyboarding skills are lacking. Okay. So that's that. That's counting in tertiary.
So that's 100.
No, well, not really. That's in tertiary, base 3. So let's look at now the basis of decimal, because by understanding the basis of the base 10 numbering system, we can understand what we need to do in binary, and this is going to provide us with the foundation to convert from decimal to binary and binary to decimal. So here I have written out the decimal positional table. So I have the powers of 10, 10 to the 0, 10 to the first, 10 squared, 10 cubed, etc. And the powers they correspond to, and we all know this, is the ones place, the tens place, the hundreds place, the thousands place. And again, when we look at a number like this, what am I doing? I'm moving from right to left. But we've been working with numbers our whole lives. We tend just to look at it and understand it left to right. So if I look at this number, 0D957. Now, I added something here, 0D, because now we're going to be working within 3 different numbering systems. Binary, which will denote 0B or preface it with that, or hexadecimal, 0X. because I can have 1 0, and that's a valid number in binary, decimal, and hexadecimal, but they're very different numbers depending on the base numbering system. So looking at this, 0D957, what is it? Well, we know what it is, right? It's 9 hundreds, 9 times 100, plus 5 times 10, plus 7 times 1, right? It's the placeholder times the positional value. Now, again, I presented this yesterday. We need to understand maximum values, least value, and range. So I presenting it a little differently. Yesterday I presented it a street with 2 digits, decimal digits. So how many houses can we put on a cul-de-sac if we have a single decimal digit for addressing? Each house can only have 1 decimal digit. Zoning, whatever, says you can only have 1 decimal digit. How many houses can I put in that cul-de-sac?
10.
10. And those houses would be numbered
0 through 9.
0 through 9, the range. So we just looked at the decimal positional table. Let's look at the binary positional table. Again, the computer is digital, can only represent 2 states, 0 and 1. Hence, everything must be in the form of binary. So we present things, again, the byte is the smallest addressable unit. So in our presentation, we correspond to that. So I have 8 positions here. So the binary positional table for 8 bits is 2 to the 0, to the 1st, to the 2nd, to the 3rd, to the 4th, all the way up to the 7th. And these positional values represent 1, 2, 4, 8, 16, 32, 64, 128. What is the range of numbers that can be represented in 1 byte? Any network engineers here? Should be right at the tip of your tongue. You've probably seen this in IP addresses or in your networking at home, and you probably just didn't recognize it, but now it's going to jump out at you. If I were to put a 1 in each one of these places, I would have 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128. It will be 255. So the range of numbers I can represent in a byte is 0 to 255. The smallest number is 0, the largest number 255. How many numbers can I represent? 256, right? 0 to 255 represents 256 distinct numbers, okay? I gave that analogy, I've been kind of harping on it. Decimal, 0 to 9, smallest 0, largest 9, but they're 10 numbers, right? So, how do we convert between decimal to binary and binary to decimal? Number 1, until you're comfortable with this, and if you become a network engineer or system administrator, this will become secondhand to you, and you probably need to do this. We'll just jump out at you. First thing in the algorithm, create a positional table and fill in with 1s and 0s. And let me go back. I kind of skipped over something. What I'm about to show you is if I take a look at this number, 957, how could I extract those individual digits? How could I extract the 9? How could I extract the 5? How could I extract the 7? What's that? Well, or actually, I could divide. And you actually gave and there are 2 different ways. A computer, what's good for a computer can be lengthy for a human. And again, we're only dealing with things in bite-size order, so quite often we can do things by inspection quicker. The way I'd write the computer algorithm would be to divide by 10, right? 957 divided by 10 is 95 with a remainder of 7. I extracted the 7. I then use that 95. 95 divided by 10, 9 with a remainder of 5. I extracted the 5. And then, of course, I could go 9 divided by 10 is 0 with a remainder of 9. So I would have extracted the 9. So just by dividing by 10, I could have extracted them, and the result would have been in the remainders. By inspection, which is what we're going to do, I could look at the powers of 10. And I could just determine what is the largest common denominator. So just to kind of be silly here, 957. Are there any 10,000s in 957? No. Okay, moving on. Are there any thousands in 957? No. Okay. Are there any hundreds in 957? Yes. Okay, 9. So I extracted the 9. I'd then move on with the 57. Are there any 10s in 57? Yes, 5. And then I'd take again the 7. Are there any 1s in 7? 7 of them. So 2 different ways. I can go right to left by dividing by 10. I can go left to right by looking for the largest common denominator. So let's take a look now. Again, going back to, I want to convert 0b, and that 0b is important. If you forget to put 0b for binary, 0d for decimal, 0x for hexadecimal, you can't communicate it. If it's on a test, it will be wrong. So what do? We have to denote the base to interpret the value. So I create the positional table, and there's no reason that you have to put 2 to the 0, 2 to the 1, 2 to the second. All you need to do is put out the powers of 2. 1, 2, 4, 8, 16, 32, 64, 128. I fill in the 1s and 0s. So correct me if I get this wrong, because I'm just transcribing, and working in binary. We'll all make errors. Okay. So what I did is I transcribed this number, I created a table, and put it into the table. Because very similarly, okay, what is this? 957, 900s, 9 times 100, plus 5 times 10, plus 1 times, or 7 times 1. That's the value. We're going from binary to decimal. All I need to do now is multiply. In this case, it's 1, so it's identity. I don't even need to do that. Multiply or add up the positional values. So binary 0, 1, 1, 0, 0, 1, 0, 1 is, well, 0, 128ths, so I'm not going to write it down. 64 plus 32, 0, 16ths, I'm not going to write it, 0, 8ths, plus 4, plus 1. 64, 32, 96, 100, 101. So the answer is 101, and I'm writing it down incorrectly. What's wrong with my answer there? Someone tell me. 0D. I have to convey what numbering system it is, right? Because 101, that looks like binary. It could be hexadecimal. And these are very different values, right? Decimal 101 is binary 011000101. So what is my algorithm? If I have to convert binary to decimal, I write out the positional table. I then copy the number, and it will always be in byte sized. I'll put the 1s, and wherever there's a 1, I add it up. That's it. Simple. Now, how do I go from decimal to binary? Well, I actually start the same way. I write out the positional values. 1, 2, 4, 8, 16, 32, 64, 128. And I'm going to move left to right, just like I showed with that number 957. So I write out the positional values, and then I look for the largest common denominator, recording a 1 where I can. Okay, otherwise I write down a 0. So let's do this. Are there any 128ths in 169? 1. Right? And I subtract, right? 169 minus 128. What do I have, 41? And I'm going to use that 41 and continue on down the line. Are there any 64s in 41? Are there any 64s in 41? No. Okay. Are there any 32s in 41? 1. So that's all I have to do is divide. That's really what I'm doing. Or I can see which one is larger, you know, because really it's just subtraction. It's just a difference. So there's 132 and 41. So I'll write it down here. 41 minus 32 is 9. Moving on. Are there any 16s in 9? No. Are there any 8s in 9? 1. 9 minus 1 minus 8. Give the answer. Tell my brain to stop working ahead. Okay. Are there any 4s in 1? Are there any 2s in 1? Is there any 1 in 1? Okay. And I can check my work. Remember how we converted binary to decimal, right? 1 plus 8 plus 32 plus 64 should equal 169. So my answer, again, do not forget, 0B to denote binary. 1 0 1 0 1 0 0 1. Now I asked everyone to read that sheet in advance. The first, the introduction, and that has some more examples for you to try. And if you use the RTF version, I whited out the answers. So try it on your own and then change the, just highlight the whole thing and change the font color to black. And you'll see the answers. The book has more examples. In the back of the book, there is an appendix on binary to decimal and decimal to binary, as well as hexadecimal. We're going to take a look at hexadecimal next. Okay. So binary, 1s and 0s, what the computer uses. Not real human friendly. So there are times when I want to look at computers' output, addresses, things of this nature, because it's all in binary, but I don't want to look at it in binary. Hence hexadecimal, base 16. So the positional values, 16 to the 0 to the first, identity, 16 squared, 16 cubed, correspond to the 1's place, the 16's place, the 256 place, and the 496. What's that? 4,096, yes. Okay. But we'll never actually go up that high. What we're going to see is there is a natural correspondence between binary and hexadecimal, where every 4 binary bits correspond to 1 hexadecimal digit. So to convert between binary and hex, and you'll almost never go straight from decimal to hexadecimal or hexadecimal to decimal. Why? Because then we're dividing by 16 or multiplying, or I'm looking for a largest common denominator. How many 16s are there in a particular number? And of course we can do that. But quite often it's easier to go decimal to binary and then binary to hexadecimal, because going between binary and hexadecimal is straightforward. So let me show you how, and then I'll show you why this works. So hexadecimal. First thing we need to do is count. We need to count from 0 to 15 in hexadecimal. Now it makes sense, and I'm just going to reuse, because that's what we do, the decimal digits. Oh, see if I can hit the right keys here. Interesting writing on the screen and trying to control the text and the cursor. Okay, now beyond 9, there is no symbol in decimal for 10. So we have to choose one. And in fact, when you look back at the decimal numbering system, arbitrarily, again, someone just chose the symbols that we now know as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're going to choose, and we'll use capitals, if I can get the caps lock to stay on, which is not working. There we go. A, B, C, D, E, and F. So hexadecimal A will correspond to decimal 10. Hexadecimal B will correspond to decimal 11. Hexadecimal C will correspond to decimal 12. Now let's fill in. We're going to count from 0 to 15 in binary.
So once you start with 9, you start with the alphabetic after 10?
Well, A, B, C, D, E, F.
Yeah.
And that's it, right? So let's count in binary. Can someone help me? I get to go first. 0. 1. Next.
2, 1, 0.
There's no 2 in binary. 1, 0.
1, 1.
There's no, remember binary is 2 states, 0 and 1. Okay. 1, 1. Why? Because we add the 1 to the least significant bit. Okay, so it's 0 plus 1 is 1. And then, of course, I bring down the 1. 1 plus 0 is 1. 1, 1 plus 1. 1, 0, 0. Okay? Essentially, algorithmically, that's the equivalent of 99 plus 1, right? 9 plus 1 is 0, carry the 1. 9 plus 1 is 0, carry the 1. But in binary, of course, we have no number 2. We just have zeros and ones. So 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. Next, 1, 0, 1. And again, this is where, if you're not familiar with this, you have to follow that algorithm. In binary, people just inexplainably make mistakes that they're never making decimal. They'll go, 13 plus 1 is 23. They'll add it not to the least significant digit, but to the tens place, just because they're out of their comfort zone. So 1, 0, 1 plus 1. 1, 1, 0 plus 1. 1, 1, 1 plus 1. Okay, and that last one was the equivalent, algorithmically, to 999 plus 1. Next one. Okay, and again, I can check these as I move. 1, 0, 0, 1. What do I have? 1's place, 2's place, 4's place, 8's place. 1 plus 8, 9. 1, 0, 0, 1 plus 1. Oh, put a space in there, or tabbed. Bad right hand there. Okay. 1, 0, 1, 0 plus 1. 0, 1, 1. Okay. Again, force yourself to use that algorithm, and your brain is going to resist. Okay. Again, we're just so good with decimal. We've been doing this forever. We can't believe anything this simple could be throwing us off. 1, 0, 1, 1. Again, what would I be doing? 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 0 is 1, then I bring down the 1. 1, 1, 0, 0 plus 1. 1, 1, 0, 1 plus 1. And lastly, okay. Now, I'm going to fill in this chart because we know I can prepend zeros, right? 0, 9 is just 9, right? Throw that 0 away. 0, 0, 0, 0, 7 is just 7. So I can add zeros. So I'm going to pad this out so that they're all 4 bits. Oh, 4, not 5. Now, for converting between binary and hexadecimal, every hexadecimal digit will correspond to 4 binary bits. And we're going to look at this in further detail in just a minute. So if I were to ask you, what is the binary equivalent, I can get a lowercase x there, of 3f? What is the binary equivalent of 3f? All I need to do is use my table, which is why I included this in my algorithm. If you're converting between binary and hexadecimal, until you're comfortable, write it out. 0 through 15 in decimal, 0 through 15 in binary, 0 through 15 in hexadecimal. So now, what is the pattern for 3? What is the pattern for f? Okay, maybe I'll put a space in there so it's really apparent. Okay, so I just used that table. That's all I did. I said, nope, OD is decimal. OB is binary. OX. No, I'm not doing that. I'm going to go back to that. Okay, right now, all I'm doing is converting hexadecimal 3f. So for the 3, I went to my table and found it was 0011. I wrote it. And then for f, I found it's 1111. And I could ask now, what is the hexadecimal equivalent for 010? And I'll separate it here. What is the hexadecimal value for that? 1010, 1110. And don't say it. Let everyone get it first. What is the hexadecimal value for 1010, 1110? Again, all I needed to do was go to my table and match the pattern. Well, what is 1010? A. What is 1110? Okay. So to convey the need to use a prefix that denotes the numbering system, what are the various values, so please work on this, please don't say it, of binary 10, decimal 10, and hexadecimal 10, and you can give it to me all in decimal. And tell you what, I get to take the easy one. What is decimal 10? Decimal 10, okay? Or maybe just for the sake of this, I'll leave out the OD. Decimal 10, of course, is 10. So what is binary 10? What is hexadecimal 10? And of course, what you use to get this would be those positional tables. Okay, so here's that binary positional table. It's the first thing you should be doing. If you have to do a conversion, write it out. 1, 2, 4, 8, 16, 32. The hexadecimal is the ones place and then the 16s place. So if I look at what is the value, the decimal value of 10, well, I have no ones and I have 1, 2. So of course, binary 10 is decimal 2. Hexadecimal 10, I have no ones, but I have 1/16. Right? Well, convert that. Okay? What if you were converting this to binary? Okay? Converting this to binary, that 1, what is a 1? 0, 0, 0, 1. What is 0? 0, 0, 0, 0, right? Every hexadecimal digit corresponds to 4 binary bits. What is this value? Because now I can go from binary to decimal. I know this is the ones place, the 2s, the 4s, the 8s, 16s. I have 1/16. So again, I can get an arrow here. There's decimal 16. or properly 0D16. And I can look further at why this works. Hexadecimal to binary. If I just take a look at the positional charts, I have the ones place, the 16s place. If I go back up to my, if I can find it, my binary positional table, right? What if I have 1, 1, 1, 1? 1 plus 2 plus 4 plus 8, 15, right? If I add 1 to it, what's the next value? 2 to the 4th, 256. If I have 1s at every place within this byte, 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128, we know the maximum value, 255. If I add 1 to 255, take a look at that hexadecimal positional chart, 256. So this works. Every 4 binary bits corresponds to 1 hexadecimal digit. I don't even have to think about the higher order stuff. I take a binary number, I cut it up into 4s, I convert it to hexadecimal, just using the 4 binary bits to 1 hexadecimal digit. Yeah. Are you talking about over here? Okay. So what is binary 1, 0? Okay. And I just didn't include the extra zeros. I could have said 1, 2. Okay. So there. Now it's in byte size. Okay. I'll take out the question mark because maybe that's misleading too. So I know that this is my, how would we convert this? If you think about this, how would we convert this? We would enumerate the powers of 2. So I'd go 128, 64, 32, 16, if I can draw 16, okay, 8, 4, 2, 1. And then I would write, copy this down in their respective values. 0 under 128, 0 under 64, 0, 32, 0, 16, 0, 8, 0, 4s, 1, 2, 0, 1s. What's its value? 2. The second one, I did just, what the purpose of this was to show the need for the prefixes. Because if those prefixes weren't there, how in the world would you interpret these? You couldn't give me an answer. If I were to say, what is 1, 0? The correct answer is, I don't know. Okay? You could not answer that. Again, computer science, discrete, precise, deterministic, which means there's absolutely no ambiguity. That's what this discipline is. Okay. So again, if I go back, if you go back to, and I'm on a screen share here, so let's see if I can get a picture, another window. Oh, that's a picture of me. You don't want to look at that. If you watch the recording, definitely don't want to look at me. It's this one here. So where this was. Lecture Module 2, Architecture, Hardware, Computer Numbering Systems. What we just did, if I can scroll slowly enough, was Binary Lecture Worksheet 2. You should have read this prior to coming to class today. Although I would recommend you do the RTF version. The RTF version is rich text format, and you can actually edit that yourself, take notes. But in the rich text format, because I do ask you to do some conversions, and I have the answers whited out, clear text. So all you need to do is highlight the whole thing, change the font to color black, and you'll see the answers. Just a way to check your work. Also in the text presents binary, decimal, hexadecimal, and it has an appendix on conversions as well. I've never liked the way that they did it because quite often it's teaching you the algorithm, which is good, but quite often we're just doing it by inspection. You know, I give you a binary number, 1, 0, 1, 1, 1, whatever. I know it's 128 plus no 64s plus 32 plus, you just do it by inspection. If I ask you to convert 129 decimal to binary, Well, there's 128 and 129, 1, right, with a remainder of 1. There are no 64s, there are no 32s, no 16s, no 8s, no 4s, no 2s, and 1, 1. So real quickly, by inspection, we can quite often do this much quicker. And what's the first step in that algorithm? Write out the powers of 2. If you have to convert between binary and hexadecimal, write out the chart. Count from 0 to 15 in decimal, in binary, and in hexadecimal. And then just chop up that binary. Every 4 bits is a hexadecimal digit, or correspondingly, every hexadecimal digit is 4 bits, and that's it. There are times my mouth can't keep up with my focus and brain here. Okay, that's it. Again, tomorrow, I will be in this classroom from 10 to 12. Please try these tonight. If you have any problems whatsoever, get here tomorrow. You need this understanding to move forward. Also, Linux Lab 2. Try to log in, follow my directions. Please do the reading first, and log in to AcadNX. If you have any problems logging into the AcadNX, come here tomorrow, okay? If you can't make it, email me. We'll do other things, but not a problem. But this course and all of computer science, if you stay up on the work, you're golden, okay? If you fall behind, you can be lost like that. That's it. Have a great weekend.
And the quiz and the Linux Lab are due Sunday.
Sunday night by 9 p.m. Yes, lecture modules are open from Monday to Sunday. And I understand life happens. If something happens, you get in a bind, just email me, and we'll make accommodations on the deadlines.